Hey everyone, welcome back to Education is Life, your go-to channel for unlocking the wonders of learning. It is me, Joed Goh, and today we're on Lesson 13 of the Arduino UNO R4 Ultimate Training Series, focusing on hardware interrupts and debouncing a button. In the previous lesson, we've discussed why using millis instead of delay is the proper way to implement timing events in Arduino code. We were able to include several components such as LEDs and a servo motor, and control them without blocking each other's time of execution. In effect, we were able to easily add a push button switch that executes a certain action when the user presses it without any delay. In today's lesson, we'll be using the same circuit to illustrate how hardware interrupts work. You'll learn how to write an interrupt service routine, which is basically a block of code or a function that responds immediately whenever an external event is triggered, in this case, with the press of a button. In addition, you'll also understand how to debounce a button to prevent the Arduino from responding to multiple presses unintentionally. And finally, you'll understand the significance of using the volatile keyword when declaring variables that are used inside an interrupt service routine. As always, before we start, a huge thanks to SunFounder for making this entire series possible. However, to keep this educational channel rolling and reach even more learners like you, your support is very important. Please note that your likes and subscriptions fuel this channel. So by hitting that like button and subscribing, let me know that you're enjoying this content. And it helps me create more videos you love. Also, if you know someone who might find this helpful, don't hesitate to share it with them. The more viewers we have, the more in-depth content I can create for you in the future. Just a reminder, throughout this series, we'll be using this amazing SunFounder Arduino UNO R4 Minima Ultimate Sensor Kit. This kit provides everything you need to build exciting Internet of Things project. So, if you're still looking for a comprehensive kit, I highly recommend checking out this product. It's available on both the SunFounder website and Amazon. Links are in the description below. So now, let's begin. For this session, you need the following materials: an SG90 micro servo motor, a normally open momentary push button switch or the SunFounder button module, 3 LEDs with 3 current limiting resistors or simply the SunFounder traffic light module, and of course, a breadboard, some connecting wires, and your Arduino UNO R4 Minima. Here, we have the green, yellow, and red LEDs connected to pins 5, 6, and 7, respectively. Then an SG90 servo motor signal wire is connected to pin 9. And finally, the button module is connected to pin 2. If you want to refresh your memory on how these components work, please check the links to the previous lessons below. An interrupt is a signal, also known as an interrupt request, that tells the processor to pause its current program execution and immediately executes a specific code block in response to that interrupt. Interrupts are built into all Arduino boards, and they are ideal for monitoring real-time events. Its job is to make sure that the processor responds quickly to time-sensitive or critical events, such as detecting a change in input. Arduino interrupts can be triggered by various sources, such as buttons, sensors, serial communication, and other peripherals. So, how does it work? When an interrupt occurs, the Arduino jumps to a predefined section of your code known as an interrupt service routine, or ISR, to deal with the event. Basically, ISR is just a function, and once that ISR is done executing, the control returns to the main program, right where it left off, and the processor returns to whatever it was originally doing. So, why bother using interrupts? The first is for improved program responsiveness. Imagine a self-driving car or a robot avoiding obstacles. Interrupts ensure the robot reacts instantly to sensor readings, enabling precise movements. The second is for efficient code execution. Interrupts allow your processor to do other stuff while actively monitoring for time-sensitive events to trigger. And third is for handling multiple events. Interrupts enable you to manage multiple external events simultaneously. For example, you can monitor a button press while still monitoring sensor data. Generally, there are two types of interrupts: hardware interrupts and software interrupts. For this lesson, we will simply focus on hardware interrupts. So, let's see how to implement hardware interrupts in your Arduino code. First, I'll show you a simple program that controls a servo motor in a sweeping motion and an LED traffic light module. This is somewhat similar to our previous lesson, except I didn't use the millis function here. Instead, I intentionally used the delay function to highlight how interrupts can provide a more responsive solution even for blocking codes. So, in this program, I included the PWM servo library. Please note that you can always use the standard servo library if you prefer. Then, I defined the servo pin at pin 9, the green, yellow, and red LED pins at pins 5, 6, and 7 respectively, and the button pin at pin 2. Then, we have the instance of PWM servo called servo1. Also, an int variable pos with an initial value of 180. This will be the initial position of our servo motor when the program runs. In the setup function, I set the modes of the 3 LEDs to output and the button pin to input. Then, this code attach the servo pin to the PWM servo instance and positions the servo to 180 degrees. This code initializes the serial communication and then a 1-second delay before executing the loop function. Now, inside the loop function, we have this for loop that iterates the pos variable from 180 down to 90 and then writes the position of the servo motor every 40 milliseconds. In addition, this code turns on and off the yellow LED alternately after every loop. And these two lines of code turn off the red and the green LEDs. Once done, there is another for loop that positions the servo motor back to its original position from 90 to 180 degrees. The codes inside are identical except for the initial and the ending positions of the motor. So now, because these two for loops execute sequentially, the program must wait for them to complete before proceeding to the next line of code, which is reading the button pin state. Here, if the button is pressed, the red LED is turned on for 3 seconds before it exits the if block and repeats the process. Again, let's see how this program works. As you can see, these for loops gradually perform a sweeping motion. The angle is changed every 40 milliseconds while the yellow LED blinks. One for loop takes about 3.5 seconds to finish. That's 40 milliseconds times 90 loops. So, since there are 2 of them, that's roughly a 7-second delay before the button pin can be read. In effect, even if I press this button when the program starts, I still have to wait at most 7 seconds for this button to be read. And there you have it. The if block finally gets executed, and we see the red LED turned on. Now, building on what we learned in Lesson 12, we know that the millis function offers an efficient way to handle timing events compared to delay. It is highly recommended to use millis whenever possible for greater control and responsiveness of your Arduino projects. However, to illustrate the power of interrupts, let's leave this code as it is. Eventually, as you write programs that handle more complex tasks, delays become unavoidable. When working with real-time data or intricate calculations, even the most efficient programs encounter processing delays. You could be fetching data from a cloud server, waiting for your sensors to reinitialize or recalibrate before reading another value, or your program could be waiting for an embedded machine learning model to analyze and predict. Now, even though your processor is super busy doing several things in sequence, there are critical codes that your processor needs to service immediately when certain events are triggered, and this part of your code cannot be delayed. This is where interrupts become very useful. So, what are hardware interrupts? In the world of Arduino, hardware interrupts are a way for external events to grab the microcontroller's attention. These events like a press of a button, or a sensor reading reaching a threshold, are detected on specific pins configured as inputs. most Arduino models limit hardware interrupts to a few designated pins. For example, the Arduino UNO has two, pin 2 and pin 3. However, some boards offer more flexibility. The beauty of hardware interrupts lies in their simplicity. To get started, you only need to complete two steps. First, write an interrupt service routine. Here, I'll call it red LED on ISR. This is simply a dedicated function that will execute when an event associated with this interrupt service routine occurs. And second, attach the ISR to an interrupt pin using the attach interrupt function. This tells the Arduino which pin to monitor and how to detect the event. The attach interrupt function takes three arguments. First is the interrupt pin. This specifies the digital pin to which the external signal will be coming from. In our circuit, that's pin 2. In this documentation, we can see three overloaded versions of this attach interrupt function. However, we will use the first implementation as recommended. Now, for the first parameter, we need to use this digital pin to interrupt function to specify the interrupt pin. So, I'll pass in the button pin, which is pin 2. Then, the second argument is the interrupt service routine to call when the interrupt occurs. That's the red LED on ISR function. The third is the interrupt mode. This identifies how the interrupt will be triggered. The common modes include low, change, rising, and falling. So, what do these modes mean? Well, let's test this one by one to see their differences. For example, when we use the low mode, the interrupt is triggered whenever the pin is low. This means that when the button attached to pin 2 is pressed at any time during the program execution, the processor will immediately shift to execute this red LED on ISR function. So, we need to implement our code here inside this interrupt service routine instead of checking the button pin to go low using the digital read inside this loop function. So, I'll cut these codes and paste them here. Also, I will not be needing the delay function call inside this ISR. And finally, I can get rid of this if block inside this loop function. So now, let's upload the code and see how it works. As you can see, the output looks the same as the previous one. However, watch what happens as I press this button. The red LED on ISR function executes immediately. It pauses the servo sweeping motion and turns on the red LED. So whenever this button pin goes low, at any given time, this interrupt service routine gets executed immediately. Now, when this function finishes, and that's going to happen as soon as I release this button, the process continues exactly where it left off as if nothing happened. I'll try it a few more times just for you to see how responsive it is even with blocking codes present in the main program. Now, if you don't like this kind of behavior, let's experiment with the different interrupt modes that might suit your specific project needs. I'll replace the mode from low to falling. This means that the interrupt is triggered when a falling edge signal is encountered, meaning when the button pin goes from high to low. Now, based on our current circuit connection, this button module is configured to use a pull-up resistor, which sets the initial value of pin 2 to high. This means that the interrupt will be triggered at the exact moment I push the button, from high to low signal. So, let's upload the code to verify the result. Now, please pay attention because it will happen very fast. Watch what happens to the red LED at the exact time I press the button. I'll try it several times for you to have a good look. As you observe, the red LED turns on for about 40 milliseconds only, and that's the effect of the delay inside this for loop. If there is no delay here, you wouldn't be able to see the red LED turning on because the interrupt service routine is triggered and executed so fast just during those exact moments when the button pin goes from high to low. To understand it better, I'll change this interrupt mode from falling to rising. This means now that the interrupt will be triggered when the button pin goes from low to high, during the rising edge. This is the opposite of the previous. So, what do we expect here? This means that the interrupt will be triggered at the exact time I release the button from being pushed. Let's upload the code and verify the result. Now, I will press the button, and as you can see, nothing happened yet. The interrupt is not yet triggered. It will not be triggered during the low signal or the falling edge. But the moment I release it, it fires. Watch it again. I'll press it, and then release. Now, there is another interrupt mode called change. When you set it to change mode, the interrupt is triggered whenever the pin changes its value either from low to high or from high to low. So, in the case of our circuit, clicking the push button will trigger the interrupt twice. During the time I press it, this changes the signal from high to low, and the time I release it, this changes the signal from low to high. Let's upload the code to confirm this behavior. Now, observe what happens as I press the button. The red LED turns on for about 40 milliseconds and then turns off as the servo sweeping motion continues. And now, watch what happens as I release the button. Again, the red LED turns on and then turns off as the main program resumes its execution. There are a few important things to consider when writing an interrupt service routine. Generally, an ISR should be short and fast to prevent interrupting the core program execution for extended periods. Lengthy ISRs might delay other program tasks. Another thing is that, as compared to other functions, ISR cannot have any parameters and does not return a value. So, typically, we use global variables to pass data between an ISR and the main program. Global variables are variables declared outside a function, like this. So, when using global variables to share data between the ISR and the main program, it is recommended to use the volatile keyword. For example, in this red LED on ISR function, aside from turning on the red LED on, I'll also set the pause variable to 180 so that when the main program resumes control after the interrupt, the servo motor also positions to 180 degrees. And now, because the pause variable is accessed by both the ISR and the main program, we'll use the volatile keyword. Also, one key benefit of the volatile keyword is its ability to prevent accidental compiler optimization. Compilers aim to create efficient machine code, and sometimes that means removing unused variables. So, if you declare a variable that isn't explicitly called in the loop or the setup functions, the compiler might see it as unnecessary and could remove it entirely. This would be disastrous. So, declaring a variable as volatile informs the compiler that this variable is important and should not be optimized away. Now, before I upload this code, I'll change the interrupt mode back to low and hit upload. So now, when I press the button, the interrupt service routine fires, and you see the red LED turns on and the pause variable is set to 180 degrees. Now, the effect of this pause variable can be seen the moment I release this button. That's the time when the control returns to the main program. And that's it. I'll test it a few more times. One common problem with hardware interrupts when used with a button is that they often can trigger multiple times for a single event. To illustrate this, I'll create another volatile variable called counter and set it to 0. Also, I'll change the interrupt mode to falling. This means that the interrupt will be triggered once the button is pushed. Now, for the sake of illustration, I'll print the value of this counter variable every time this interrupt service routine executes. But just a reminder, please refrain from using the serial.print or the serial.read inside an interrupt service routine because both operations might take too long to execute and could cause problems that are difficult to trace. Anyway, for the sake of discussion, let's upload the code. Now, let me open my serial monitor first. So, pay close attention to the serial monitor each time I press the button. So, what's causing this? Well, this happened during the process of pushing the button. Don't be fooled by a simple button press. While it seems like a single action, the internal components can make contact multiple times before registering a stable state. This is referred to as bounce. And these bounce can cause issues with our code. Luckily, we have solutions. Hardware-wise, adding an RC filter can smooth out the electrical signal and eliminate bounce. Alternatively, we can solve it through code. Here's how it is done. By using millis, we can ignore further interrupts for a brief period after the first one is triggered. To understand what I meant, I'll modify this program and add another volatile unsigned long variable called prevTime and initialize it to 0. Then, in the interrupt service routine, I'll enclose all these codes with an if statement saying, if the current time minus the previous time is greater than or equal to, let's say, 1/4 of a second, then allow these codes to happen. And then, set the new value of the previous time to the current time. If you want to refresh your memory on using the millis function, please review the lesson 12 of this course. The link is in the description below. So, this is how you should understand the logic. The moment the button is pressed, the falling edge triggers the interrupt for the first time. This interrupt service routine fires right away, executing the code. However, if the button mechanism bounces for a few more milliseconds before registering a stable state of low, this if block will protect the code from being executed again, if it is less than 250 milliseconds. Why? Because it is unlikely that you can press a button twice in less than 1/4 of a second. Thus, the succeeding interrupts must be from the bouncing effect of the button, and we can simply ignore this. And that's it. You can always adjust this value depending on your project situation. Now, let's upload the code and see if it works. Again, pay close attention to the serial monitor each time I press the button. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and it looks good. You can try it yourself. So, for your challenge activity, try to improve this program by adding a button at pin 3 and configuring it as another hardware interrupt. When the button at pin 2 is pressed, the red LED turns on and the servo resets to 180-degree position once the button is released. On the other hand, when the button at pin 3 is pressed, the green LED turns on and the servo resets to a 90-degree position once the button is released. Again, thank you so much for joining me in this lesson on hardware interrupts and debouncing a button. If you found this lesson enlightening, give it a thumbs up, subscribe to join the learning community, and don't forget to ring the notification bell so you never miss a video. Again, keep learning, keep experimenting, and always remember, education is life. See you in our next lesson. Happy coding!